Hey, are you ready for another math review? Math Review 4, the remath. Well, this week there's actually not a whole lot of math to go through, so this is going to be a really quick review. And as always, Math Review is like kind of a misnomer because we're also going to review filter concepts. So, sorry, I guess it should be called Math and Filter Review, the remath filtering, but whatever. So, we want to talk really quickly about filters. The first one I'm going to talk about is a high pass. Oh, great. Is a high pass filter. I've improved my handwriting. So a high pass filter is going to be one that allows high frequencies to pass. I mean, that's kind of a super easy definition, right? So let's say this is 20 hertz and this is 20,000 hertz. This is our amplitude 0 to 1. This is just going to be frequency down here. Okay, so a high pass filter might look like this, where this is effectively at 0. I'm drawing it slightly above so you can see where it is. And then the high frequency is going to pass. So very literally, it just allows high frequencies to pass, and it attenuates the low frequencies. You can contrast this with a low pass filter, which is going to look exactly the opposite. It allows the low frequencies to pass, and then it attenuates the high frequencies. So that's a low pass filter. The low passes. Okay. So now, the last one we want to talk about is a band pass filter. And that's going to look something like that. Essentially, what you're doing is you're allowing a band of frequencies to pass through, some band. You can have a narrow band or a wide band. Let me do this slightly differently so I can show you the difference. So here, this would be a really wide band. So it's a wide band pass filter. It looks like maybe everything between 50 hertz and 17 kilohertz is coming through. You can also have a low or a narrow pass filter, narrow band, I mean, a narrow band filter that might look like that, where you just allow very little bit, a very narrow band to come through. So that's a narrow band pass filter. This might be everything between like 10,000 and I don't know, maybe 12,000 is what that looks like. So really we're only allowing 2,000 hertz to pass through that. And the other one we're allowing, 10,000 hertz to pass through or more. So those are different types of band pass filters, high band, low band, which would be called high pass, low pass. And then this band pass filter, which is not strictly as descriptive because it could be anywhere, it could be any band. All right, so another thing that came up this week was we know how to compute this. So we want to look at maybe the frequency n for a tube with one closed end, which is going to be 2n minus 1 multiplied by the speed of sound over 4L. And often what we're given here is we're given the what harmonic you want to look at. You're given the n, and you're given the length of the tube. You've done this a few times, so we could just say, what is the length of the first harmonic, or rather the first resonant frequency, I should say, for a tube with length of 0.85 meters, right? So this is simple. We want to know the first resonant frequency, the length is 0.85, so F sub 1 is going to equal 2 times 1 minus 1 multiplied by 340 over 4 times 0.85. Simplify, 2 times 1 is 2, minus 1 is 1, so it's just going to be the same. It's, multiplying by itself. What we've now got here is 340 over, I've done this so many times you'd think I'd remember it by now. Like I've done 4 times 0.85. It's 3.4, and so 340 over 3.4 is 100. So our first resonant frequency is 100 hertz. So you've done this in the past, but what you're having to do in this module is kind of flip it around the other way. Use the same formula, but now what you're given is the resonant frequency. I'll just abbreviate that. Oh, that looks like it had some trouble in its life. So there we go. So you're looking for the resonant frequency. It's the same formula, right? I mean, you could write it as 100 equals, and then we're going to assume that it's always the first resonant frequency that we're looking for. So we can assume that it's 2 times 1 minus 1 multiplied by 340 over 4L. We don't know what the length of this tube is. You can write it the same way, and you can, try to solve it. So this is going to end up being, this 2 times 1 is 2, minus 1 is 1, so we can get rid of it. 340 over 4L. And then what you can do here is you can then take the 4L and multiply both sides by 4L. So this kind of migrates over here. So then what you have, let me make a small cut down the side of this so we can continue our math. What you are going to have is 400L equals 340. Then you'll divide both sides by 400. You have L equals 340 over 400, which should be 0.85 because we're using the same numbers. 340 divided by 400, 0.85. So you can figure out that L is 0.85. This is very easy, but it's easy for some of us. It's not necessarily easy for everybody, especially if you have, math anxiety, or it didn't really click going through math about how to move the things around and end up at a different number. So what I'm going to do is I can walk us through how to come up with a different formula. It's the same formula, but it's moved around. And you can just write that down in your notes. And so this will come up on the exam. And if you know this formula and you know how to move it around, go ahead and use this formula. If you are not very good at moving things around, I'll give you a new formula that you can put into your notes. So this is written correctly. So what we're going to do is we're going to very slightly rewrite this formula. So you know that, let me choose red. So when you have 2 times n minus 1, this is implied that this is over 1, right? Anything over 1 is itself. So you can always rewrite, like, you can rewrite 8 as 8 over 1. You could rewrite a happy face as happy face over 1, and it's still the same thing. So we're going to rewrite 2 times n minus 1 as 2 times n minus 1 over 1. And then what we're going to do is we're going to combine these two mathematical terms. We're going to combine this and this. So those are going to be combined. And what we're going to end up with is, what? Sorry. What we're going to end up with is an error message, I guess. What we're going to end up with is 2n minus 1. Oh, let me make sure I'm still recording. Is that what that was? No, we're still good. I have no idea what that was. All right. So we're going to end up with 2n minus 1 multiplied by 340 over 4L. So, 1 times 4L is just going to be 4L. So we can kind of ignore that one. It's still there, but it's been multiplied. So now what we can do is we can then distribute this 340 throughout the rest of that formula. That's going to equal 680n minus 340 over 4L. Now we can divide both of these by 4, and we can end up with a different, a better, and more concise formula. So hang on one second. I got to use my calculator. 680 divided by 4 is 170. So we'll have 170n minus 340 divided by 4 is 85. 170n minus 85 over L. Remember, I've been not writing this, but this equals Fn. Okay, I'm going to erase some things so I have some more room to work, but this is what we're going to keep for now. All right. So we want to get L by itself. What we're going to do is, no, we don't want to get L by itself. But we do want to get L by itself. Sorry. We want to get L by itself. So what we're going to do is we're going to multiply L on both sides. We're going to have Fn multiplied by L equals 170n minus 85. And now we still want to get L by itself, so we're going to divide by frequency, divide by frequency, and there you go. We'll just erase these. And there's L by itself. L equals 170n minus 85 over the frequency. So let's test this out. We'll use the numbers that we just used in the previous frequency. So we know that L is what we're looking for. L equals 170. Now remember, N is going to be the first resonant frequency, so we can say that it's 170 times 1 minus 85 over, and here we're given that it's 100 hertz is the first resonant frequency. So 170 times 1 is 170, and 170 minus 85 is 85. We end up with 85 over 100, and I mean, wouldn't you know it, 85 over 100 is 0.85. So 0.85. And that's what we wanted. We wanted the length, and we've got the length. So if you're bad at moving your numbers around and computing things that way, then the formula that you want to put into your notes is this one right here. L equals 170n minus 85 over the resonant frequency that you're looking for. If it's the first resonant frequency, then it's probably what you're given. So this, you'd write it as 100. And then since it's the first resonant frequency, you're going to put a 1 there. Usually that's what you're going to be looking for in the exam. That's what you're going to be looking for. But in practice, outside of this class, you might be looking for a different one. Or later on in another exam, you might be looking for the third resonant frequency for you know what? Maybe I will have that be an exam question. So I'll tell you that the third resonant frequency is blah hertz. And so then you're going to have to know that you put 3 in there if I tell you it's the third resonant frequency. This formula will still work out. Let me get rid of the red stuff again so you can write it down in your notes without being confused. L equals 170n minus 85 over the resonant frequency. Okay, great. There's one final thing that we need to go through. And that one last thing is, well, before I do that, I guess I need to erase some things. The last thing that I want to go through is you're going to have a complex tone, which means you'll have a fundamental frequency. So you're going to be given a complex tone with a fundamental frequency of, let's say, 250. Now that's passed through a filter it's passed through a tube, I should say, not a filter. Well, we could do either one. Maybe it's passed through a filter with a high pass. Yeah, let's do that. It's passed through a high pass filter. And what's going to be passed is anything above 600 hertz. My computer's freaking out again. There we go. So we're going to pass anything greater than 600 hertz. What does that look like? That could be a question on the exam. You're going to have to draw this. Well, first of all, you need to draw what does it look like to have a complex tone with a fundamental frequency of 250. You're going to have a harmonic here, 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 and so on. It'll be 250, it'll be 500, it'll be 750, it will be 1,000, and it'll be 1250. Mental math game is struggling today. So then your high pass filter is going to filter out anything below 600 hertz. It's going to pass anything above 600 hertz. So the output will look like this. This is where 250 should be. This is where 500 should be. There's nothing. And then 750, 1000, and 1250 are there. Because the filter came in boop, 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 and then it allows that to pass. So there's your high pass filter. You could do the same with a low pass or a band pass. It'll say that what's passed is frequencies like, let's say, all frequencies between 400 and 800 are passed, and so you would have an output that is just 500 and 750. But the actual tricky one is when you have a complex tone with a fundamental frequency of 250 that's passed through a tube with one end closed, our typical one closed end. Since we've been working with a length of 0.85, and by now we all know that the first resonant frequency is 100 hertz, we're just going to use that. So the first resonant frequency is 100 hertz. The second resonant frequency is going to be 2n minus 1, right? So 2 times n is 4. In this case, we're looking for the second resonant frequency, so 2 times 2. That's 4. Minus 1 is 3. So the second resonant frequency is 300. The third resonant frequency, 2 times 3, is going to be 5. 2 times 3 is 6, minus 1 is 5. So that'll be 500 hertz. And if we wanted to know the fourth one, it would be, I'm going to write it up here. 4 times 2 is 8, minus 1 is 7, so it would be 700 hertz. So you're going to have to draw the first 4 resonant frequencies, the output of a complex tone with a fundamental frequency of 250 hertz that goes through a tube with one end closed of a length of 0.85 for the first 4 resonant frequencies. What does it look like? Well, the way that I would do it is I would first draw out my complex tone with a fundamental frequency of, here's 250, 500, 750, 1000, 1250. Okay, that's beyond where we're going to need to be. 250. I said that my handwriting got better, but I feel like I'm lying to you. So we're going to do it 2.5, 5, 7.5, 10, 12.5. You know that it's 250. Just multiply it by 100, I guess. Okay, so here's your complex tone. Now we're going to pass it through this filter. And what I like to do is I like to draw the filter over this. So our first resonant frequency is at 100, which is down here. Boop. And the next one is going to be at 300, which is about here. The next is at 500, which is here. And the fourth one is at 700, which is about here. You know what? Let's blow this up a little bit. This is too small. So we'll stop at 750. Whoops, I accidentally erased the P. That's makes funny jokes. All right, so 250, 500, 750. Now what I do is I will draw in the frequencies for my tube as well. So I know that 100 is about here. That's 100. 300 is going to be about here. 500 is here. 700 is here. So now we can draw this in. And the computer is freaking out again. There we go. Sorry about that. Okay. So this is what our filter is going to look like. Our tube filter is going to look like this. It'll start curving back down here. So our output is going to be, let me choose a third color. Our output is going to be the complex tone multiplied by the filter that we've just drawn in. 250 is going to get hardly anything. If I was going to draw it out, I might give 250 like just this tiny bump. It might be at the point where it gets nothing. It might be at the point where it gets just hardly anything. 500 is all the way through. In fact, it might even be amplified above where it was because it hits right on the third resonant frequency. 750 is going to be slightly attenuated like that. So this is the answer right here. This is what you'd turn in. Label your axes: 250, 500, 750. This is the output of a complex tone with a fundamental frequency of 250 passing through the first four resonant frequencies of a tube with a length of 0.85. Cool. All right. So this should help you on the exam. I guess I don't need to erase that. I'll just get rid of this slideshow in a minute. So that should help you on the exam. The exam is going to go up soon. You'll have a week to do it. And if you have any questions, send me an email and I will answer it. Okay. Good luck and talk to you soon.